Yes, good morning, class. In the last lecture, we have discussed about different feedback amplifier configurations. We have seen that there may be voltage series configuration, voltage shunt, current series, and the current shunt. Also, we have discussed about the voltage series feedback configuration, and we have applied the input over there for the non-inverting. We derived there the values of your gain with feedback, input resistance, and output resistance. Similarly, in the today's lecture, we will discuss about voltage shunt feedback amplifier, and we will apply the input to the inverting terminal, so it will be an inverting amplifier case. So let us start to draw the diagram. So this is my operational amplifier, and we are going to have here the case of feedback amplifier with voltage shunt. Voltage shunt means the output will be taken in the form of the voltage, and it will be sent back to my input in the shunt, means in parallel. So how I will connect it, this is important. So if I draw a negative feedback over here, so this is my simple negative feedback, where I'm going to use these two resistances RF and R. So it means whatever the voltage, for example, if this is my V naught, or if I'm taking this load resistor RL, so definitely this will be across load resistor R will be my voltage V naught voltage, or the output voltage. So this voltage with respect to this point and the ground must be sent back to my input. So look here, what I am doing here at my input, if this is my inverting terminal and this is my non-inverting, as this is inverting amplifier, so I will directly connect it to the ground. No need to connect it with any resistance. So this is my voltage V1 and this is voltage V2. So this is my voltage V2, which will be fed into the non-inverting inverting terminal, and the voltage V0 plus my input voltage, as is in the case of inverting amplifier. So definitely I will apply an input. For example, plus minus V in is the voltage which is applied in inverting terminal. So this voltage plus the voltage which is being sent back from the output into the input must be in parallel. So how that they will be in parallel? Look here, if this is my one voltage, and if I look at this output voltage V0, it means this voltage must be divided across these two resistances R1 and RF. And look here, this is one point, another point is ground. So if I connect this point also with respect to the ground, can I say these two are in parallel? Or if I connect this ground, or if I have a common ground over here for these three, one is this ground, second is this one for this V1 also, and third is this one. So they are all connected to a common ground. Let this be that ground. So it means this is that one terminal and the other terminal is connected to V0. It means this input voltage and the output voltage V0 are connected in shunt or in parallel. And similarly, this voltage is sent back. It means it is a voltage shunt feedback configuration. Is it clear? So now similarly, as we have done in the last lecture, we will consider here the value of current I in, and we have few notations, that is open loop voltage gain, which is represented as A. So I will not repeat that. You just kindly go to the previous video and look at how we have obtained these values. So A is nothing but V naught by VITP. I will simply repeat it over here. AF, which is the gain with feedback, it is equal to V naught by V in, and third gain is the beta gain, or simply the B feedback gain, which is equal to the VF upon V0. So we have used these three values. So I will start with the closed loop voltage gain, or simply the gain with feedback. So first I will derive the closed loop voltage gain. So to derive this voltage gain, what I need first, I need the value of the current that is going in this branch or in the RF branch. So let this be the IF, and you know that I in is the total incoming current. At this node, this current must be divided into two parts. So right now I am assuming that this is the current IB2, which is going inside this terminal. Practically or ideally we say that there is no current that is going inside this terminal, or IB2 is equal to 0, where we consider I in equal to IF. So we'll do this same thing over here, but just for your understanding, I told you that I in is divided into the two currents IB2 and IF. So I can write here that I in is equal to IB2 plus IF, where I can write as I in is almost equal to IF, because the reason is we have assumed that no current is entering, and the reason behind that is we have a very high input resistance over here. The value of Ri is very high. In the case of ideal, it is infinity. That's why we consider in the ideal case IB2 is 0. But due to the very high value, this IB2 is very small. So can I say here that as Ri is very large, we can assume that IB2 is very small, or simply I in is equal to IF. Now, if I apply here my KCL at node V2, at this node 2, I will apply KCL. So you know how to apply the KCL. We assume total currents going outward. So I in will become equal to minus I in. IF will be outward, so it will remain same, and IB2 is 0. So if I have to find value of I in, or if I write here, if I apply, we apply KCL at node V2. But we will assume that total current, this current is I in is incoming. I can write it as minus of I in plus of IF. It must be equal to 0, or simply I in is equal to IF. There are many ways of writing this KCL equation. So simple one is this: incoming current is I in, outgoing is IF, because IB2 is almost equal to 0. Now what is the value of I in? If this is the voltage V in and this is the voltage V2, can I say the difference of these two voltages, where this is assumed to be high in comparison to the other voltage V2, because the direction of the current is from this to this. So can I say I in can be represented as V in minus V2 divided by R1? Look here, what I am saying, that I in can be represented as V in minus V2 upon R1. And similarly, IF is the current going from V2 to V0. So can I say V2 minus V0 by RF will be my IF? So it is equal to V2 minus V0 by RF. Right? So let this be equation number 1. Also we have, okay, we can write here one more thing that I have left, that VID is equal to the difference of the non-inverting and the inverting, that is V1 minus V2. Now look here, we have here A is equal to V0 by VID. So can I write it is equal to V0 by V1 minus V2? What is V2? It is some voltage, I don't know about that. But what is V1? Definitely it is 0. So can I say that this can be written as, I will not write here, it is equal to V0 by minus of V2. Can I write like this? So I will substitute these values and we will see that what we will get. So as I said that V2 is equal to, or I said that A is equal to V0 by minus of V2. So I will use that. I said A is equal to V0 by minus of V2, or in the other way, we can say that as I want to put the value of my V2 in this V2, I want to substitute my value in terms of A and V0. So what I will write here, this thing implies V2 is equal to minus V0 by A, and I will substitute it in this equation. So what I will get, it will be V in minus V2 will be minus of V0 by A. Can I write it as plus V0 by A divided by R1, and it is equal to minus of V0 by A minus of V0 by RF. So by solving this, I will get the value of the ratio of V0 by V in, and it is equal to, it will come out to be around minus A RF upon R1 plus RF plus A times of R1. Now look here, what is V0 by V in? It is the output voltage divided by the input voltage. So V0 by V in is nothing but equal to my AF, or the gain with feedback. So I will simply write here it is equal to AF, and I can further minimize it as I can say as R1 plus RF is very less than A times of R1. I have already discussed in the previous lecture that why it is there. A is in the 10 to the power 6 range, R if is in the range of 10 to the power 3, if I assume it to be in kilo ohms. So this product will come out to be around 10 to the power 9. And these R1 and RF, if they are in the kilo ohms, definitely they will be in the range of 10 to the power 3. So definitely 10 to the power 9 is very, very greater than 10 to the power 3. So I will assume that this are very small, and I will neglect these two values. So I will get AF is equal to minus A times of RF by A times of R1. Because R1 plus RF is neglected in comparison to the AR. So A will be cancelled out, and you will get the closed loop voltage gain in the case of voltage shunt feedback amplifier for the inverting case is equal to minus RF by R. It means this negative feedback, the gain is now depending upon these two voltage, these two resistances RF and R1. And in the earlier case of voltage series, we have seen that gain was equal to 1 plus RF by R1. So now over here, the A is not there, means the gain 10 to the power 6 or open loop gain is not there. Depending upon the values of these two resistances, which we have connected, that is RF and R1, they will decide that how much gain will be provided to this circuit, or this input will be amplified with that value. Is it clear? Now to further rewrite this and to get few more conclusions, I will rearrange these terms of AF, or this term where I have got this value. So I will rearrange these two terms as we have done in the previous case. So I will write here that AF will be equal to minus A times of RF. I will divide the numerator and denominator with the value of R1 plus RF. Why I will do that, you will come to know now. Divided by R1 plus RF divided by R1 plus RF. Now look here, in the denominator we have R1 plus RF plus A times of R1. So this is divided with R1 plus RF, and similarly AR1 is also divided with the value of R1 plus R. So this is the same thing. We have just rearranged few terms to get some few more conclusions. So we'll get here. If I look here, this RF upon R1 plus RF, can I name this as K? So I will get here minus A times of K divided by, this is 1 plus, this is A, and what is R1 upon R1 plus RF? We have obtained in the earlier case, in the previous voltage series case, we have obtained there that this R1 upon R1 plus RF is nothing but equal to beta. Right? So what we will get here, in the place of R1 plus RF, I can write here B, where I can write here where K is equal to RF upon R1 plus RF and beta is equal to R1 upon R1 plus RF, where beta is the gain of the feedback circuit. Beta is my gain of feedback circuit. And in some of the books you will find that this K will be denoted as your attenuation factor, or simply the voltage attenuation factor. Voltage attenuation factor. And you will find this value will be always less than 1. K is always less than 1. The reason is you find here RF divided by R1 plus RF, so definitely denominator will be always greater than the numerator until unless R1 is equal to 0. जब तक R1 greater than 0 रहेगा, ये value हमेशा K की less than 1 रहेगी. Right? So this is about the current gain, voltage gain with the feedback, and we have seen that this feedback current gain is represented in the form of open loop gain and the feedback gain also for the feedback circuit gain. So it is equal to minus AK upon 1 plus AB. Right? So now next we will find the input resistance with feedback. What is going to happen to our input resistance? Input resistance with feedback. What is the value of input resistance without feedback? It is Ri. But when we are applying the feedback, definitely the input resistance will change. So what we have to do, we have to now see our diagram. If I go back to my diagram, you can see here in this diagram, this RF is connected to both input terminal and the output terminal. So now to find the input resistance, I need to separate, or I want to find the effect of this RF at the input. So I need to find here, or I need to divide here RF in input and the output. So how we do it? We have here a Miller effect. I will make use of the Miller effect over here. You can search it on the internet what Miller effect is. So this Miller effect is used to separate these feedback resistors which is connected to both output and input terminal. So what I will do here, I will separate my values. So how we'll do it? Let me draw a diagram for better understanding of this. Now operation amplifier. Like this. And if I draw the internal circuitry also over here for better understanding, it will be an input resistance Ri over here. Definitely an output resistance will be there R0. This equivalent circuit, we all know how we came to this circuit. And we have a voltage source AVID over here. Right. Now, this is my output resistance RL, across which I'm going to get my output voltage V0. Now, if I look at this input resistance, that is R1 also there, which was connected to a voltage source plus minus, let this be Vin, sorry, and this is R, and this non-inverting terminal was connected to ground, right? We use here V1 and over here we use V2. Now this is the circuit. Now if you compare this circuit with the circuit that I have drawn, this one, the only difference is that I have not connected all the grounds together, and second one is that I have not used this RF now. Now this RF has to be divided between the two, or simply at the input and the output. So how we will divide? By using the Miller effect. By using the Miller effect. RF can be broken down at two sides, input and output. So at input it will be RF divided by 1 plus A, and at the output end it will be RF into A upon 1 plus A. So these are the two different values. So I will simply connect one resistance over here which is connected to ground. So this is one resistance at the input side, and similarly one resistance will be there at the output sides, whose values are determined by this Miller effect, and it says these are RF upon 1 plus A, and it is RF into A upon 1 plus A. So now we don't need to look into this output terminal as we are finding only the input resistance over here. So if I have to find the input resistance, if I assume here current I in, so definitely this input resistance with feedback, if I denote it with the RF, must be equal to, or RIF I must say, that is input resistance with feedback, it must be equal to V in by I in. Or simply if I take this circuit, in a box, that is all the circuit with feedback. So up to here, this is my input. So look here, अगर मैं इस point पे check कर रहा हूँ, so what will be my value of resistance? That is nothing but my Ri. So this is what I have to find. So I guess it is clear to you what is input resistance with feedback. If there is no feedback, definitely this resistance R1 and RF upon 1 plus A is not there. Then the input resistance is only R1. But when they are added, definitely they will also have an impact on the input resistance, and that is what I have to find. So it is easy to see now in this diagram. As you can see that this is ground. So can I connect these two grounds together? Yes, definitely I can connect them together. Now look here, there is one resistance RF upon 1 plus A, and second resistance is Ri. These two resistances are there. Are they connected in parallel? because their one terminals are connected at V2 and other terminals are connected at ground. So can I say these two are connected in parallel and this combined combination is connected in series with the R1, because one terminal is connected over and other is not connected to the ground, it is connected to some voltage V in. So definitely this R1 is in series with the parallel combination of these two resistances. So can I say directly here that my RIF, it is equal to R1 plus parallel combination of RF upon 1 plus A with RI. So this is the value of my input resistance with feedback. Now look here, RI value is very large. It is very large. In ideal cases it is infinity, and A is also very large. So can I say that as A and RI are very large? So I will write here that RF in parallel combination, RF 1 plus A in parallel combination with Ri will be almost equal to 0, or you will get the conclusion that your input resistance with feedback is equal to, means now your input resistance has reduced, it is equal to R1 in the case of voltage shunt feedback, whereas in the voltage series we have seen it has increased. वो क्या हो गई थी वहां पे, इंक्रीज हो गई थी, राइट? याद है किसी को कितनी होगी थी वहां पे वैल्यू? We have seen there that was increased with the value of Ri into 1 plus AB, right? Now, next we are going to discuss the output resistance with feedback. So third case is output resistance with feedback. So what is this output resistance with feedback? Nothing but the resistance that we will see when we look from the output. जब हम यहाँ से देखेंगे तो जो हमें resistance मिलेगी, that will be my output resistance, and we will consider here my total feedback circuit. So how we will calculate, let's discuss it now. I will draw the diagram. This diagram I want to make a small change just for your understanding, just for better understanding, I must say. What is that change? That non-inverting terminal I'm shifting to the upper side and inverting to the lower side, means this circuitry or this plus circuitry will be shifted towards upper side and negative circuitry will be shifted towards the lower side. So this is what I want to make changes here in my circuit. So if this is my input resistance without feedback, this is positive terminal, this is negative. So positive is directly connected to ground, so I will draw here ground, whereas negative is connected with some feedback resistance. RF and one series resistance R1 with the voltage source over here. This is my V, right? Plus minus. And we have output resistance over here. So this is my normal circuit, right? If you want, yes, we will draw here the value of R0 and a source connected over here. You know the value of this source, it is A times of VI. This is Ri. Need not to write because we are not concerned here now with the input. So you know how to find the output resistance with feedback. We have just discussed it in the case of voltage series also. Whenever we have to find the voltage series with feedback, what we need to do, we have to replace our independent sources with the internal resistance. It means if we look here, there is only one independent source, that is this one. This source will be replaced with the its internal resistance, or simply it will be short circuited. So this will be short. It means this V in will be equal to now 0. इसकी value को हमने 0 कर दिया. Now one more thing, at the place of my RL, what I'm going to do, I'm going to connect my voltage source over here. So I will remove this part and in place of this I will connect a voltage source. Why am I going to connect a voltage source? Because I need to find here the ROF value. So this will be now my V naught. So I will find here the value of ROF. Definitely due to this voltage source, some current will flow inside it and I will name it as I naught. This I naught will at this point break into two parts. So I will name these two currents as IA and IB. And this resistance is R naught. Okay. So I will write here that my output resistance with feedback will be nothing but equal to V naught by I naught. The second thing is that my total current I naught, assume it equal to IA plus IB. Now, as we have done in the earlier case, look here, this is one resistance RF and this is other resistance R1, which is, you can see here now come in parallel with the RI. Look here again, this is one point which is connecting my R1 and connecting my RI, whereas the other terminals of RI and R1, can I say, are both connected to ground. RI ground से connected है, R1 भी ground से connect हो गया because we have shorted this input voltage V in. So due to this, can I say that RI is now in parallel with R1, one thing, plus this combined combination is in series with RF. If I look at this branch, this is one resistance RF which after it is going in parallel to this. So the combination is somewhat like this. मैं इसको यहाँ ड्रॉ करूँ तो ये कुछ इस तरह से कॉम्बिनेशन आपको मिल रहा है. This is Ri, this is R1 and this is RF. So I want this resistance because there is one branch IB current through which it is flowing through this branch, and this branch is having this resistance RF series with the parallel combination R1 plus R. So I will write here this is my one branch resistance. And if I look at the other branch resistance which is going in this path, over here there is only one resistance R0, and you know the R0 value is very small. So can I say this value is very greater than R0? If the resistance in this branch is very large, if the resistance in this branch is very large in comparison to R0, can I say that my IA current will be very greater than IB? Or from this, can I say that I can assume my I naught to be almost equal to IA because IB is very small due to the value of the high resistance faced by it. So now using this concept, I'm going to apply the KVL at the output loop. What is my output loop? This is my output loop. I'm going to go from here to this ground. So this is my output loop. I will apply KVL at this point. So you all know how to apply the KVL. I will write here. Apply KVL at output loop. What we will get? We will start from here. This is a voltage source. So I will write here V naught is equal to, what are the drops over here? There is only one drop across R naught and other is this voltage AVID. So I will write here the drop across R naught will be R naught into the current IA. So it is R naught into IA, and you will find this voltage plus minus, so it will be plus AVID. So from here I will find the value of I naught. In place of IA, can I write I naught? So I will write here V naught is equal to R naught I naught plus AVID, because we have already assumed that I naught is almost equal to IA. So we will get this. So from here I will get the value of I naught. I naught will come out to be around, if you rearrange these terms, it will be V naught minus AVID by, this is my value of I. Is it okay? Now what is VID? We all know what is VID. If this is voltage V2, this is V1, so definitely this difference of these two voltages is VID. So we have VID is equal to V1 minus V2, where V1 is connected to ground. So can I say VID is equal to minus V2? Right? So I will write this value of minus V2, or you can also write it as VF also, but I will use here minus V2. So it will be equal to V naught minus A times of, what is VID? I will write here minus of V2 divided by R. So I will get here I naught is equal to V naught plus AV2 by R. Now, what I have to do, I have to find the value of ROF. What is ROF? ROF is nothing but the ratio of V naught and I naught. It means I want a equation where only V naught and I naught are there. But in this one, I have I naught, V naught, but V2 is there. I need to remove this V2. So how I will remove it? This is important. So if I go back to my diagram and see what is V2, it is the voltage at this point, or simply the voltage across this resistor R1. So if I come from here, this is voltage V1, V0, and if I follow this path, can I say that this voltage V2 is nothing but some part of V0, and by the voltage divider rule, I will say it is equal to R1 into V0 upon R1 plus R. So by this formula, I will convert my V2 to V0 and I will substitute it here. So I will get here V0 plus A times of V0 into R1 upon R1 plus RF divided by R. Right? So with the help of this, I will get I naught is equal to V naught plus A. If I look here, what is R1 upon R1 plus RF? Can I write it as B? Yes, it is B V naught divided by R. Now take the values of V naught by I naught and get its ratio. So it will be V naught by I naught will come out to be equal to R naught upon 1 plus AB. Now, this is important. Look here, without feedback, my output resistance was only R naught. But with feedback, this is the value of ROF. So with feedback, my output resistance has now reduced with the value of 1 plus AB. So it's a very good thing. This feedback has reduced my output resistance. We want our output resistance to be very small. So this is my third formula we have obtained for the voltage shunt feedback, right? So in the last, this is all about the voltage shunt. In the last, I want to discuss one more thing, that is a bandwidth with feedback. So we all know that there is a gain bandwidth product and it always remains constant. So I want to discuss this bandwidth with feedback effect. Means how my bandwidth is going to affect when we are having the feedback. And definitely we are having here the negative feedback. We have discussed both these cases with the negative feedback. We know that the gain bandwidth product is a constant. Gain into bandwidth is always constant. It means whenever we are going to increase the gain, if this gain is increased, definitely there will be decrease in the bandwidth. Or in the other case, if I say that gain is decreased, definitely the bandwidth must increase because their product has to remain constant. Now in this case, if I look at this, here the gain is reduced because we are using the negative feedback. Right here, because of negative feedback, gain is decreased by a factor of 1 plus AB. This is a very important factor. We will use it in a lot of cases, especially in the case of oscillators. We have a criteria over there. We make use of this criteria. We will discuss there. But this 1 plus AB is very important. You have to remember all this, whatever we have derived, that is the input resistance or the output resistance. So it must be remembered with reference to 1 plus AB, that how 1 plus AB is going to increase it or decrease it. So as I said that in the negative feedback, gain is reduced. So definitely if gain will reduce, definitely the bandwidth will increase. Or can I say from here that if I take my bandwidth or the frequency with feedback, that must be equal to F into 1 plus AB. Because gain has reduced, so definitely my bandwidth has increased. So this is the important relation. If we get some numericals, like they may have given us the bandwidth without feedback and they have given us the values of A and B, and they may ask us, just tell us that what will be the value of your bandwidth with feedback. So with these formulas we can easily calculate everything, right? So I will stop here.